Greetings. First of all, I appreciate the opportunity to be at this Congress. My name is Rosalio Reyes, and I am going to talk about of my work, fractional model for the study of tuberculosis in Mexico. This work is done in collaboration with several authors, as you can see. Let's start by talking about fractional calculus. The fractional calculus generalizes the differential and integral operators to non-integer orders, which is why it's also called generalized calculus or arbitrary order calculus. This idea is as old as calculus itself, but its development has been largely conditioned by the absence of a convincing physical and geometric interpretation. Mathematicians such as L'Hopital, Leibniz, Abel, Euler, and Fourier, among others, have addressed the question of a derivative or integral of fractional order. This branch has a true development until the second half of the 20th century, which is why we find here a classical and, at the same time, a modern branch of mathematics. Fractional operators are non-local operators. That is, what happens at a point depends on an average in an interval that contains the point, and this makes the fractional calculus an exceptional tool for non-local phenomena, such as ecological process, accumulation of metals, population evolution problems, radiation problems, economy, etc. Over time, there have been many proposals of derivatives of fractional order. Among the best known are the definition of Riemann-Levy and the definition of Michael Caputo, which are the ones shown below. These definitions lack quite useful properties. For example, the definition of Riemann-Levy does not satisfy that the derivative of 1 is 0 when alpha is not a natural number. Both definitions do not satisfy an analog to the product rule for two functions. They also do not satisfy an analog to the formula of the derivative of the quotient. There is not an analog to the chain rule. And finally, the definition of the derivative of Caputo requires that the function be differentiable. For this talk, we will consider a derivative of fractional order, which is defined as follows. Given an interval I, a positive real number alpha, and a positive continuous function t on I, the local generalized fractional derivative of f of order alpha at the point t, denoted by gt alpha of f, is defined by the expression 1. The positive function t is usually known as the kernel. If the kernel t is equal to 1 when alpha is a natural number, then we obtain a conformal local fractional derivative of any order. If the kernel t depends on t when alpha is a natural number, then we get a non-conformable local fractional derivative of any order. As an example of a conformal derivative, we have the following case proposed by Colin. Here we have that the kernel t is defined by this expression, and alpha between 0 and 1. Note that if alpha is equal to 1, then we have the classical definition of a derivative. And this last definition can be generalized by the expression 2. In this case, alpha is any positive real number, and the kernel is defined by this expression, which is equal to 1 when alpha is a natural number. Note that if there is a neighborhood of T for which the classical derivative of f of order n is defined, then this definition gives us the classical derivative of order n of f at T. As an example of a non-conformable derivative, we have the following case proposed by Guzman. In this case, the kernel is given by this expression and alpha between 0 and 1. Now, let's see some properties of the definition of local fractional derivative. Recall that d at n is the derivative of order n. The first properties provide us with a way to calculate the generalized derivative in relation to the kernel T and the classical derivative. Also, the following properties warranty use some familiar properties of the classical derivative for the differential operator. For example, the linearity. We also have rules for the product and quotient of the functions. These properties are similar of the usual derivative. And finally, we have that the differential operator of a constant is 0. Another property of the differential operator is an analog to the chain rule, which is given in the following relation. When we using a differential operator, it's also natural to think of an integral operator that has certain properties. In this case, we will use the following operator. Note that A must be in the same interval as T. Both operators have a property analogous to the fundamental theorem of calculus. This property will be very useful. Well, on the other hand, the Gompers model is one of the most widely used sigmoid models, adjusted to ground data and other data, and is perhaps only surpassed by the logistic growth model. It was first suggested and applied by Benjamin Gompers in 1825. This model adjusted to the relationship between the increase in the death rate and age, and this relation was called the average exhaustion of man's power to avoid death. The usual industry first quickly began to use this method of projecting the risk of death. Researchers have adapted the Gompers model to everything, from plant growth, animal growth, the growth of tumors and bacteria. Today the literature on this subject is huge. In the 60s, Lair, for the first time, successfully used the Gompers curve to feed tumor growth data. In fact, tumors are cells populations that grow in a confined space, where the availability of nutrients is limited. It's useful to write the Gompers curve as follows. Note the expression of the Gompers differential equation. Now we consider the Gompers differential equation using the differential operator Gt alpha, given in the expression 4. This expression has a solution y in t given in the expression 5. For the proof, we consider that alpha is between 0 and 1, and we will use some terms that we have mentioned previously. First, we consider that the integral operator j is given by the following expression. Also, we consider that the logarithm in the differential operator is equal to the following expression. We will use the theorem analogous to the chain rule previously mentioned. The reason for this is because y and t can be seen as the composition of two functions, f and g, given by the following expressions. Taking the derivative of f and evaluating in j, we obtain the following result, which is y in t. Now we will calculate the differential operator g on the function g in t. For this, we will make use of the following theorem. So, when we apply the differential operator, we have that is the product of the kernel by the derivative of the function g, which is an exponential function. And in the integral operator, we use the fundamental theorem of calculus. Then we simplify and note that the resulting expression is the previously mentioned logarithm. So, when we apply the differential operator, we obtain the desired result. Finally, if we have a problem with initial value, then we take c equal to y in t sub 0, and so we end the proof. Now, we will start the Gompers fractional model using the kernel t given the following expression. Note that by using this kernel, we are dealing with a conformable fractional derivative. And the solution to the fractional equation of the Gompers model using this kernel is given by y in t in the following expression. For our purpose, we will consider the fractional derivatives of Caputo and Cali given in the following expression, as well as the classical derivative. First, we make a comparison on the behavior of the function using the same parameters. We can see that the Cali derivative best approximates the classical derivative. Now, we give an application of this fractional model to a tuberculosis study. Data were taken from a percentage of population in Mexico with tuberculosis. These data are represented by the black dots. Using Bayesian theory, the parameters that best approximate this data for each case we estimate. And to show which is the best approximation, we calculate the error L1, and in this case we observe that the smallest error is for the generalized fractional derivative in blue. In fact, the error in the other approximation is more than double than in the case of the generalized fractional derivative with the kernel t. In conclusion, we usually use models with derivatives of an integer order since they have a better physical interpretation. But fractional order models can also provide a very good fit, as in this case and other models. It's all. Thanks for your attention.